Welcome back to ECE 442-542. Judging from the attendance, it looks like we just had an exam. I will try to return those exams after class, not before, just so you stay focused. And what you need to focus on now is exam number 2, which is not too far from here. It's before spring break. That's the idea behind that exam. And it will be covering material on homework 3, which is actually due a week from Thursday, but you already have all the material, I believe, to work homework 3. And homework 4 will be on discrete equivalence. And there's additional material if you want to try to read a little bit. It's somebody else's notes on discrete equivalence. What we want to do today is get into that topic. I'll try to motivate that with some block diagrams. And then we will probably spend most of today dealing with zero-order hold equivalence, or systems, plants that are preceded by a zero-order hold. And hopefully that will start to become clear as we go on. We'll look at some particular systems preceded by a zero-order hold and try to find this G of Z. Now we're trying to find transfer functions in the Z transform variable, G of Z. And how do we get there? There are other ways to do discrete equivalence, and those are numerical integration and pole zero mapping. Here's basically a description, or one quick way of talking about discrete equivalence. We're trying to convert continuous time systems, and those systems could be, and here the highlighting has relevance. The yellow is emphasizing certain things, and I guess that's a blue. Maybe I should have chosen a different color, but the blue is correlated with the other systems. We could be trying to convert filters or controllers that we already have. Maybe we have a fifth order analog filter and we want to implement that with a computer or with a microcontroller. How do we obtain from the filter transfer function, capital C of S, how do we get the capital C of Z? And then you know how to put that into a difference equation and run the numbers or program that into an algorithm that you could then generate these filtered responses given an input noisy signal. Or you might have already taken a controls class, or maybe somebody gives you a controller and they say, oh, you've had a digital control class, can you implement this controller in our computer? So how do we take the controller, capital C of S, that's maybe an analog-based controller, and convert that into a discrete time controller, C of Z? Again, once we have capital C of Z, you know how to generate a difference equation for that capital C of Z. Or we might want to analyze a design, or we might want to actually design a digital controller explicitly in a discrete time system, and our plant is actually an analog plant or a continuous time plant. We might then have this capital G of S, and we need to find the G of Z, capital G of Z. And that's what we will be focusing on first, and those are what we will call zero-order hold equivalence, and hopefully it will become a little bit more clear what we mean by zero-order hold as we go through today. Another way of thinking about this, I know you're just dying to figure out what was happening on one of your homework assignments when you had to use this C2D function. You were converting continuous time to discrete time, and basically what we are talking about with discrete equivalence is the background material to understand what C2D as a function is doing in MATLAB. You can include various arguments in this C2D. You could say, well, I think it actually defaults to the zero-order hold. But you could say, oh, give me a tungsten approximation, or give me a forward, or give me a backward. I feel like a cheerleader now, so you're going to have to start standing up and giving me all these forwards and backwards and tungstens or bilinear or ZOH. You'll be coming in to class with ZOH on your shirt now, right? That stands for zero order hole. Let's then get into this first by block diagram, trying to understand the big picture of what's happening, and let's just remind ourselves of what we have or could have at this point or maybe a little bit later in this class, and what is this block diagram for a continuous time control system. Here is our reference input, R of S. And that then, when it gets compared to, and let's say I have negative feedback, a signal that's maybe related to our output, and we'll have to clean that up in a minute. But here is then the controller. You may or may not feel comfortable with that as a transfer function in terms of designing it. If you've already had a controls class, you maybe know what that capital C of S is. If not, stay tuned. We'll figure out how to do that. Here is our plant, or the system that we are trying to control. That could be a car's suspension, it could be an aircraft's dynamics, longitudinal, maybe lateral, it might be a rocket, it might be something else, a electrical system. And here is the output of that combination, and we actually might have some additional external inputs that we may not even have any control over. That's a disturbance input, and we may not even be able to control that, but we need to design the system so that it's responsive to, or maybe doesn't respond to, that disturbance. We then actually might have a noisy output measurement, and so we model that by putting some noise onto that output signal. And we may or may not be able to measure that output directly. We may have to have some kind of sensor dynamics, or we might even have some additional control processing in the feedback path prior to connecting that up and comparing that with our reference input. This is now our, I'll just call feedback dynamics. This is noise, and this is our output. And we are really wanting to make this system behave the way we want it to. And we'll design that capital C of S and maybe buy or design sensors or dynamics for H of S. We may be given G of S, or maybe we get to design G of S also. If we do, then you may want to design G of S to make this process easier for you to do. This is our continuous time or analog controlled system, and this really should be sort of burned in your head or into your brain, maybe not in your head. Maybe you can have some shirts with this on it, right? Your G and your C and your H. You now have this system. There's really two things that we may want to put into a discrete form. We may want to convert C of S, and or we may want to convert that plant. And there are two different reasons for doing that. But let me just write that down as far as what we may want to do. There's two main reasons. or situations for discrete equivalence. One, as I said before, is we may want to convert controllers, or maybe you just have a filter that you designed in 320A and you want to put it into a computer. Now you have this fifth order Butterworth and it has a particular bandwidth, maybe it's low pass, and you want to now realize that in your computer and not have to bug Josie for the parts to create that. Now you can simply create a difference equation representation of that filter. So you're wanting to convert controllers or filters, which I will try to be consistent with and say maybe I'll call those capital C of S to C of Z's. And maybe that's because you can program better than you can solder. Just joking, just kind of. But maybe you want to be able to adjust your controller or your filter coefficient more than you want to desolder and redesign an analog filter. That's one reason we might want a discrete equivalent. Another reason would be if we wanted to convert the plant or plants from their analog version, capital G of S, to their discrete time form, capital G of Z. And we may do this because we want to either perform some discrete time design, build a capital C of Z directly, or we may want to analyze that. Controlled system in a discrete setting. Let's now look at a couple of different block diagrams that now start to incorporate this conversion of continuous time to discrete time. And I'm just going to call these simplified, but I'm hoping this starts you thinking about what it is that's happening. The first one I'm going to suggest is what we'll say is a sampled system. Let's say that we now have our reference signal that's maybe analog still, and it creates an analog error, E of S, but now we want to actually sample that error signal, or we want to convert from analog to digital. So we put it into an A to D converter. Coming out, then, we have this, in the frequency domain, a transform in the Z domain of our error signal, because we can apply the Z transform to a discrete sequence of values. Then we can process those discrete signals through our discrete controller to create, let's say, a Z transform or frequency domain input waveform. But if this is now driving an analog plant, we can't just hit that analog plant with a sequence of numbers, 5.2, every time we sample. We have to give it an analog waveform in order to drive this system effectively. So you may think of a motor and now you're trying to apply a voltage to that motor to keep it spinning or to spin it at a particular velocity. Well, you can't just apply a voltage of 4 and then quit, and then 4.2 and quit. It's an analog motor. It's not going to like that. It wants to have this continuous waveform applied to its terminals. So we need to now convert that sequence of numbers, the digital sequence, into an analog stream so that it can now, and you can see that I'm actually neglecting some of the other pieces, the disturbance piece, etc., and maybe I will forget what's in the feedback path, but now we have a sampled block diagram, this now being a sampler, and this getting us back from a discrete sequence into an analog formed signal. That's what we will say is a hold sequence. Yeah, or hold. Thank you. So the question or the correction to my notes was that signal at the output of the plant is a continuous time signal that gets fed back and compared to our continuous time reference signal to generate a continuous time air signal. And then we can sample that, and then we're good to go. Thank you. Questions on that? And in this one, maybe what we are interested in is this design of capital C of Z. And here we only really have one sampler, and maybe we'll have that in just the other case also. But let's look at another block diagram. Here is, I will say, a block diagram that's more related to working completely in a discrete time environment. Here, suppose that we actually have our reference signal as a sequence of numbers, R of Z, which is now in the transform domain. We can then drive that, let's say that our output is also going to be discrete time, but we'll get there in a minute. That can now be processed directly with this discrete time controller, C of Z, but we may still have an analog plant. If that's the case, then we need to convert that sequence of values coming out of that controller into an analog waveform. Now we can apply that analog signal to our analog plant G of S, but in order to compare this output of the plant to a sequence of numbers that are our reference input, we actually need to sample the plant output, and now we have this discrete time system, and we'll have it even better if we can figure out how to replace all of this with a G of Z. And this, here again, is our hold device. This is our sampler. But now what we want to be able to do is figure out, if somebody gives us a G of S, how do we get a G of Z? That's what we want to talk about today. That's our zero order hold equivalent. Somebody's given us a G of S, and now think of your DC motor. Think of a mechanical mass spring damper system. Think of an automobile. Think of the temperature in this room. Maybe we're trying to control that. That has some G of S description. We want to now describe that with a capital G of Z. So let's now look at that. So this is now our zero order hold equivalent discussion. And this is a subset of this broad class of discrete equivalence. We have the above block diagram, and if we extract from that the piece that we're really interested in, we now have, let's say, u of z, which is right here. Then we go through a digital to analog converter, a zero-order hold. That now produces, let's say, an analog waveform, which can drive an analog plant. And there are particular relationships or labeled signals, and we want to now find a transfer function that will go from an analog transfer function to a discrete time, which is preceded by a zero-order hold. And this is different. So somebody will say, oh, you have a system. You need to now know, is that system a plant, which is preceded by a zero-order hold? Then you do a particular discrete equivalent. You do a zero-order hold equivalent. We'll then talk later about just going for giving us a filter and saying, give me a discrete equivalent. We'll do that a different way. We won't necessarily have to precede that filter with a hold device. We'll just go from a C of S to a C of Z. Now, in order to figure out what capital G of Z is, let's look at how we can model. We know what G of S is. I'm going to assume somebody gives us that. Now let's look at the dynamic behavior of a zero-order hold and an A to D converter. Let's find their characteristics. If we can then model those, we can put it all together to find a way to determine capital G of Z. That's our objective. Let's now examine the characteristics of the A to D, the analog to digital. This is on the output side of the plant in this above diagram, most recently sketched diagram. And let's look at the digital to analog, and we will actually today and probably most of this semester just concentrate on a zero-order hold, and that's on the input side of our plant. This is our D to A conversion process by means of a zero-order hold. Let's now look at the first one, the A to D characteristics, the analog to digital behavior. This one's pretty hard, so you better pay attention. Suppose that the output looks like this. Here's Y of t in an analog form. Then if we actually sampled this, we would then have to figure out what our sampling period was, and I'm maybe exaggerating what that is, but I couldn't draw it fine enough resolution anyway if I picked a smaller sampling period. But let's say there's t, 2t, 3t. If we now say what happens when we go from this analog waveform to a digital waveform, all we're really doing is taking those blue dots, where now t is replaced by just a sampled set of values on the horizontal axis. We now have t, 2t, etc. And you can use your imagination that I'm trying to make those the same. And we want to know what's the dynamic relationship between the analog, the continuous time, what kind of dynamics exist in going from y of t to, let's say, y of nt over here. And I said this was really, really difficult. What are the dynamics? How is this processed? You just sample, you just pick it, or don't you? You just take it. There's no dynamics involved. So this is a pretty easy relationship, or pretty straightforward characteristic. There are no dynamics, and so really we don't have to worry about the back end side, the analog to digital piece of this whole process. And that's why it's called the zero order hold equivalent. We really don't have to worry about the back side, the output side. Let's now look at the zero order hold characteristics. Here, let's say now that we have a discrete sequence of numbers. Let me say that that's u of n, and maybe these are, getting tired of drawing dashed lines, so I'll just make solid lines. But here's 2, whoops. Wow. Maybe I should just draw dots, but this is trying to emphasize that that's just one instant of values. Now if we process this with a zero order hold, what we're saying is whatever this value was at time step 0, we want to just hold that. We don't want to do any kind of shaping of that value. We want to just hold it flat, zero order. It's not a linear or first order. Then we might be looking at some slope relationship between the first and the next one. But now it's a zero order. There are no real dynamics between here and there, but it is going to give us some dynamic properties. We are going to just hold it right here so that now, if we look at this in the continuous time setting, we now are going to be constant there, constant there, constant there. Is that clear what we're doing now? We are just, whatever we have at a particular sampling period or point, sample, we just hold it until the next sample. And then somebody gives us another number, 4.2. We just hold that for the next sample. Then they give us a 5. We just hold that for the next sample. That's all we're doing with the zero order hold. But now this does introduce some dynamic behavior. What's the time response behavior associated with that zero order hold? And how have we sometimes characterized or described properties of a system? What do we typically maybe do to obtain the behavior of that system? We kick it, we excite it, And we might want to excite it or kick it with something that's fairly easy to do. What if we just applied a unit pulse to this zero order hold, this behavior? And a unit pulse is what? It's just 1 at time 0. So let's now apply a value of 1 and see what happens. If this is now what I've done, I've applied a value of 1 at the origin in time, and now I'm going to say this is my pulse response of the zero order hold, and this is going to be an analog waveform. Well, what we agreed to do with the zero order hold was simply whatever you give me, I'm going to hold that for 1 sample period of time. So if you give me a 1, a unit pulse at 0, I'm going to just hold that until the next sample period. And this would be the unit pulse response of a zero order hold. Now, how do I describe this? Or can you describe G sub ZOH in terms of elementary functions? And what is G sub ZOH of T? If somebody asks you, what is that picture? What would you say? Looks like a pulse, doesn't it? And we know how to describe a pulse or model a pulse in terms of elementary waveforms or elementary functions, and in particular, steps, unit steps. G sub ZOH of T we could describe as U of T, and that would just keep going and going, but we need to turn it off, and we can turn it off 1 time step later, 1 sample period later, and that's now the behavior or a model of this unit pulse response of a zero order hold. That's pretty straightforward, I hope. You can see that that's, okay, that looks consistent with what we said our zero order hold was going to behave like. Now, we want to incorporate that into our capital G of S, which means, oh, let's just take it into the frequency domain. So that now, if we Laplace transformed this unit pulse response, we can now look at it in the frequency domain. And now this is pretty straightforward. We just have to remember how to model or Laplace transform a step and a step with a delay. I'll do the hard part. G, capital G, that was the hard part, going from lowercase to capital. That's what happens when you Laplace transform, right? You take the time domain or continuous time into the S domain, and now what happens? What's the Laplace of a step, unit step? Right? 1 over S. Now, what happens when we have u, little u of t minus capital T. What's that Laplace transform? If you forget, you could say, wait a minute, that kind of looks like just a unit step, right? You could say, oh, that's a 1 over s, maybe with something else, and that's correct. It's 1 over s with something else, and that something else is what happens when you delay. Did everybody get that? If you're looking for extra or partial credit, you would say, well, I know it's this with something. Well, that with something is an e to the minus ts, right? Where t is the sample period. Or that now has a 1 over s in 2 spots, so I could now maybe rewrite this and say, oh, that's just 1 minus e to the minus ts 1 over s. And this is now a model, a frequency domain model of our zero-order hold, the way it's going to behave. That means that we can re-sketch or redraw our block diagram. We now have, we don't just have to say ZOH, we can now say G sub ZOH, and we know what that is. That now precedes a plant, whatever that plant is, G of S. Then we go through basically this non-issue, this analog to digital, and create what we need. The combination of the D to A, G of S, and the A to D is the G of Z that we want. Now, what we're going to have to do, though, is sort of break this up. We said the A to D doesn't really do anything for us, but now what we can do is, let me label this, and now you'll have to just sort of try to pay attention to the notation that I'm going to be using, because eventually we will just sort of throw all that away. That'll just be too much to keep track of, and we'll just sort of do a shorthand and say, oh, G of Z is this. And we'll just sort of agree that this is how we define what we mean by that. But here, y sub capital Y sub 1 of s is now going to be 1 minus e to the minus ts over s times g of s. And this piece right here is really just the Laplace transform of the unit pulse response of whatever our system happens to be, whatever that capital G of S is. If we applied a pulse at the left-hand side and processed it through that combination of blocks, that signal would be capital Y sub 1 of s, which would be the response of our system preceded by a zero-order hold when we apply a unit pulse to that system. All right, now we have to find out what we're doing. We now have an expression for this capital Y sub 1 of s, and that's this 1 minus e to the minus ts times G of S over S. Or we could put that into two separate pieces and say, oh, I have a G of S over S minus an e to the minus ts G of S over S. Now, what we want to do is sample that and then take the Z transform of those samples. That's what we need. The sampling is because of this A to D. Meaning we now need to take, if we inverse Laplace so this is basically what we're going to do. Here is the result that we need, capital Y sub 1 of S. If somebody inverse Laplace transforms that, that will give us a little y sub 1 of t. Then if we sample that, that will give us a sequence of numbers. We can z-transform a sequence of numbers, and that's what we want to do. We're going to now sample this after we've inverse Laplace transformed it. And we know how to inverse Laplace transform g of s over s. We just put another s in the denominator of whatever g of s was. We'll have to figure out what we do here, but this is just a delayed version of g of s over s. So we could just do those two terms, sample them, and then find the z-transform of that sequence of numbers. Is that clear what we're trying to do? Let me try to describe that notationally or develop some notation, and then like I said, I'll just throw all of this away and we'll just agree that this is all buried in the process. G of z, this is what we want to end up with, is the z-transform, and that now these dashed verticals, that's my sampling process. I'm now going to inverse Laplace transform capital Y sub 1 of s. That's going to give me a little y of t. I'm going to sample that, meaning this is some continuous time signal. These vertical dashed lines are the process of sampling with the A to D. And then the piece after I've sampled this continuous time signal, I end up with a discrete time signal. So here is a discrete time signal that I can actually z-transform. That's just a sequence of numbers, and I can now take the z-transform. That's that infinite sum. And we just put in the appropriate values. Now, like I said, you may not want to be playing with this all the time. These dashed vertical lines, this script L, y sub 1, let's just agree, to define that away. So let's just say that capital G of z, now by definition, when we do this zero order hold equivalent, that's what that triangle means. Now I'm defining it. I'm going to just say that if we can sort of agree that what's happening now, the dashed vertical lines, the script L inverse, which means the inverse Laplace transform, we're going to just simplify all of that and just say notationally, let's just call it like that. Is that okay? So that Z is pretty heavily used. It's a lot's going on, but we're sort of burying it. Okay? Now, if that's the case, we can now break that up into two pieces if we want to. We can z-transform using that same agreed to notation. We had the first piece. It's a linear operator still, all of those processes. And now we simply need to be able to z-transform g of s over s and e to the minus ts g of s over s with the agreed on process. Now, we can actually make our life a little easier if we remember what e to the minus st or e to the minus ts was in the z domain. e to the minus ts corresponds to a delay, doesn't it, of capital T units of time. So note that e to the minus ts is the Laplace transform of a delay of, let's just say, t seconds. Let's say that's our unit of time. In the z domain, how do we model a capital T units of time delay when capital T is a particular length of time, isn't it? It's one sample period. So now in the z transform domain, the z transform of a t second delay that's just z to the minus 1. That means that instead of having to worry about this e to the minus ts, we can actually pull that outside the z transform and say, oh, we're just going to delay that result by one sample period. Whatever is inside that's remaining, and that's g of s over s. Meaning, now we can say that g of z is going to be the z transform of g of s over s minus z to the minus 1 g of s over s. Oh, this is looking better. Now we have just one thing to transform, g of s over s. So that now capital G of z is 1 minus z to the minus 1 z transform of g of s over s. We've derived it. We don't have to rederive it. I'm waiting for the question. Do we have to rederive that on the test? No, you just have to be able to use it. That's why I told you, when's the next test? Since we're in the spring semester, and if we're sort of 4 weeks apart, we're in February and March, keep the same numbers. Our last test was on the 12th of February. The next test is on the 12th of March, my brother's birthday. So I'll have to remember that, right? So I'm reminding myself, better remember that date. I'll tell him to watch this video. How far in are we? All right. What we have just done then is derived this zero order hold equivalent. And I have 12 brothers, so it's hard for me to remember. No, I'm just teasing. See, it seemed like 12, I'm sure, to our parents, but pulse response transfer function is what we will call this, or some people might call this, or the zero order hold equivalent. And we now are agreeing that that's going to be this capital G of z is 1 minus z to the minus 1 z transform of g of s over s. So if somebody gives us or tells us what the system is, what the plant is, they've given us capital G of s. We now put one more pole at the origin. We add a s in the denominator. We give it another pole at the origin. And what does that do, really? Well, we haven't talked about it unless you've taken an analog control class, but if you put a pole at the origin, that makes your control process or problem a little more challenging. But if we can z-transform that combination, then we just have to scale it by 1 minus z to the minus 1. And that's pretty easy. Let's do it for a few plants, just so that you get the idea of how this process works. So let's look at some examples. And what we do typically when we're learning something new is we start slow, right? When you're learning how to walk, well, maybe you start crawling first, right? You probably didn't start sprinting. If you did, maybe you ended up with a gash on your forehead, or luckily I have hair in the back of my head that covers up that big hole that happened in the back. Never mind. Example. Let's suppose that somebody gives us a very challenging system, 5. It's just a gain. Suppose that somebody just gives us a system that corresponds to a gain. What's that going to look like when we find capital G of Z? Let's go through the process and see what falls out. We're now saying that we want to precede our G of S with a zero order hold, sample that, and produce this G of Z, which is really going to be the zero order hold equivalent of a pure gain. Or they might call this, the G of Z might be referred to as the pulse response. That's what happens if you hit it with a pulse and you've now preceded your plant with a zero order hold. This is now the pulse response transfer function in some books or in some descriptions. The formula is capital G of Z is 1 minus Z to the minus 1. And now we need to Z transform G of S over S. But G of S wasn't very complicated, was it? That was just a 5. Well, that 5 I can pull out front. And this is now I need to Z transform a unit step. Or I could rewrite that 1 over Z. I could say this is 1 minus 1 over Z. And remember what we're doing inside this Z curly brackets? We're inverse Laplace transforming whatever it is, 1 over S. That's now just a line or a constant 1. We sample it, and now we Z transform that sampled sequence of numbers. And what happened when we sampled a unit step in the discrete time setting? Do you remember what the transform of that was? You should already have all of those rows on that table that I gave you memorized. Row number 6. In the Z transform table, that was this Z over Z minus 1. But this, if we put that over a common denominator of Z, what do we get in the numerator? I have Z over Z, that gives me the 1, and I simply have the minus 1, and this was scaled by 5. Wow. So what happens when we find this capital G of Z when our plant G of S started out as a gain. We get a gain back. Seems to make sense, right? If we now have a gain in the analog system, we precede that gain with a zero-order hold. Oh, good. We get the same kind of system behavior in the discrete time case. It's always nice when you can start to feel sort of comfortable with what you're doing. All right, let's shake that up a little bit. Let's go back to our physics, and now let's look at another example. Suppose that now our system is a pure mass. So suppose a zero-order hold precedes a pure mass system. Picture. I keep thinking that if I practice enough, it will get better, but I guess if you practice poorly, it doesn't help, right? So I need to concentrate, and I'm sketching. So there's my zero-order hold. Here is a system that's now more than just a gain or a constant. That's actually this G of S, which is our pure mass, and we want to know what is this going to be. Where are the poles, the zeros, etc. Just as a review, let's derive what G of S is. So we, free body, yeah. Have a lot of bodies. We have about 50, and no, not quite. We gave a test, didn't we? So we lost a few bodies. So I erased that last body, right? Didn't need a two-body problem. We just wanted a free body diagram. Which is, we now have, now my box is something else. This is now a mass. And suppose that I apply to that mass a force. That's my input force, and I'll just call that U. So this is my U is overused, isn't it? I use it for the unit step. I use it for a generic input. Now my input U is actually a force. And I need to draw a line in the sand. Here's my position, X. There's 0. And I want to know how is X related to U dynamically. And I'm doing this because hopefully it's not too far away in terms of memory. What do you remember about physics and a mass and its dynamics? What happens when you apply a force to a mass? It starts accelerating, doesn't it? So F is equal to ma. And what is acceleration in terms of position? We differentiate it twice, don't we? And we get our acceleration. That's why we took our calculus in 8th grade, so we could do physics. So that we now have F is equal to ma. There is our time domain description of the dynamic behavior of our system. But we can solve that now for x double dot. That's equal to 1 over m u of t. And I'm going to get tired of writing 1 over m, so let me just say that that constant is an a times u of t. There is our system dynamics. X double dot is AU. That's in the time domain. We can now find the transfer function. We wanted the capital G of S. If we're dealing with transfer functions, we don't have to worry about initial conditions. What happens when I Laplace transform a second derivative? Now I have an S squared. I Laplace transform a first derivative, I get an S. I do it again, I get another S. So now I have S squared capital X of S is that constant A times the Laplace transform of U of t. And now I can solve for my output variable, maybe, which is the Laplace transform of my position, capital X of S. That's now A over S squared times U of S. And this piece right here in square brackets, that's my plant. That's my system. It's just A over S squared. Where are my poles of that system, pure mass system? I have two right at the origin. I have two poles at the origin. Where are my finite zeros? Finite values of S that cause G of S to go to 0. I don't have any finite zeros, do I? How many infinite zeros do I have? How many infinite values of S cause that to vanish? I could let S go to infinity this way or that way. I've got two, don't I? That's where zeros equal poles, always, if you count infinite zeros and finite zeros as a quantity of zeros. So if you're interested, if you read, oh, my zeros, the number of zeros always equal the number of poles, well, that's if you allow for infinite poles and zeros. Typically, we only talk about finite poles and finite zeros, but in these discrete equivalents, we are going to need the understanding of an infinite zero, because we will map those to certain places. This now has two poles at the origin. Is that very easy to stabilize? It's right on the stability boundary, isn't it? And if you simply fed output feedback around that, if this was the classical controls class, you would just increase the frequency of oscillation, but you wouldn't stabilize those at all. Those two poles wouldn't move into the left half plane. So you would just make a faster and faster oscillator as you cranked up the gain K. Maybe not a good thing. Now, we want to put that into our zero-order hold equivalent expression. We now have G of Z is equal to 1 minus Z to the minus 1 Z transform of G of S over S. We now have 1 minus Z inverse. And what was capital G of S? That was A over S squared. Now we need to Z transform A over S cubed. So what are we doing now? Now we need to inverse Laplace transform A over S squared and sample it, and then Z transform those samples. Do you remember what happens when you inverse Laplace transform something over S cubed? What was 1 over S? Inverse Laplace transform of 1 over S, constant, right? It's 1. 1 over S squared, a ramp. 1 over S cubed, quadratic or parabolic. But we have to remember that this actually starts introducing some factorials in there. So what you need to remember is that the inverse Laplace transform of, let's say, 1 over s cubed is now t squared over 2 factorial. And 2 factorial is 2 times 1, so that's just 2. But in general, if you had 1 over s to the fourth, it's t cubed over s, or 3 factorial, or 6. Now, we need to sample that. And what you'll see in your table is maybe this t, but it may be k capital T quantity squared. We can find that in one of the rows of our table. We need to just remember that we have to scale it by that 2, and in so doing, we can now find that z transform of t squared, which is k capital T quantity squared, and that will now give us 1 minus z to the minus 1. The a can come out, and the 2 can come out, and now I will just plug in the z transform of t squared, which is, and I'm going to include the sample period, capital T, t squared z plus 1 over z minus 1 cubed. But remember what this first factor corresponds to. It gives me a z downstairs and a z minus 1 upstairs. I have an a over 2. I have a t squared z plus 1, and now I have a z minus 1 cubed. Now I can start cleaning this up a little bit. That z, this gives me 1 fewer of those, and now I have a t squared over 2 z plus 1 over z minus 1 squared. Just to give us something to, well, if I made this really trivial and said, what if my mass was 1 kilogram, then what's little a become? 1. That was 1 over m, so a becomes 1. And what if I picked a sample period of 1? Then I get rid of most of that in the front, and I end up with, so this is now my g of z in general for, what was that? That was a pure mass. And what happens if you hit a pure mass with a force? It just keeps going and going, doesn't it? That gives you this t squared behavior. And what is this going to correspond to in terms of poles and zeros in the z-plane? Let's just get rid of some of those by saying, let's say that if m is equal to 1 kilogram, then a is equal to 1, and let's just, for grin, say that t is equal to 1. Then my g of z, my zero order hold equivalent of a pure mass, becomes 1/2 z plus 1 over z minus 1 squared. And we are going to start to get comfortable, I hope, with sketching pole and zero diagrams in the z-plane, because if you've learned how to sketch root locus or root loci in the s-domain, the rules are the same for sketching in the z-domain. We'll learn those maybe in this class. I haven't decided yet. But if you've had 441, you know how to sketch root loci. But where are the poles and zeros of this transfer function, of this system? That was too vague. Where are my poles? I have two poles at 1, don't I? So here's a 1, and I usually just offset those, but you know they're right on top of each other. Do I have any finite zeros? Now, comparing that to G of S, how many poles did we have? Finite poles. We had 2 at the origin. In the S-plane, the origin is S equals 0. Remember our relationship between S and Z? It's not what I wanted. That's our relationship, isn't it? If S is equal to 0, what's that correspond to in the Z-plane? E to the 0 is 1. So those poles at the origin in the S-plane map to 1 in the Z-plane, and that makes us feel pretty good. That's really the right place, because that's right on the stability boundary, isn't it? Our stability is the unit circle. They're still right there on the boundary. Now, what did we have about zeros in G of S? We had 2 zeros at infinity, didn't we? We didn't have any finite zeros, but now, look at what happens. If we think about the unit circle, in the Z-plane, that's actually where the imaginary axis in the S-plane maps into the Z-plane. So that infinite distance up the axis actually maps around to -1. So that's basically like a 0 at infinity in the Z-plane, Z equal -1. That's something that's happening very fast. If you had a pole there, what would happen? If you just had a single pole at -1, positive, negative, positive, negative, wouldn't it? And it would keep the same value all the time. But it'd be just shaking back and forth. Every sample would change sign. Infinitely fast. Now, if we wanted to sketch the root locus of this, if we put this in a closed loop setting, you remember your root locus, it would come out here, and then you'd have 2 branches, but you're now unstable if you put this in a closed loop system with just a gain. Before, we could shake it, or we could put it in there and we'd have an oscillator, which isn't very stable, but now we're unstable if we close the loop on this system with just constant output feedback. But we'll get there eventually. But now that's another 0-order hold equivalent. What if we looked at a pure integrator? We've looked at a constant. We looked at basically 2 integrators. That's a pure mass. What if we step back and sort of look at just a pure integrator, and maybe we'll look at a exponential system. What are their 0-order hold equivalents? And we'll start to build up this feeling for what capital G of Z's look like relative to what G of S's look like. Those are our 0-order hold equivalents. Are there questions on that?